Hi all, I'm Remo, and I'll be presenting the first paper today. Um, uh, I'll be talking about the formalism for optimal planning with dynamic heuristics, and this is joint work with Florian Pommerening, Clemens Büchner, and Malte Helmert. So before we get started, let's talk about the setting. As Patrick mentioned, it's very classical, and in this case also optimal planning. And we are trying to solve this problem using heuristic search. And the interesting thing we're adding in this talk is dynamic heuristics, and you'll hear in a minute what we mean by that. And to start off, we're starting on Brisen, my favorite mountain peak. And what we're trying to do is fly down using our paraglider. And luckily, we are not just we have some agency with our glider, and we can steer, for example, but we cannot decide to go up. We can only glide down because we're very unpowered aircraft. So if we want to extend our flight, we will have to find some way to gain some altitude. And we can do that by finding some pockets of warm air that will rise and give us some more height to continue our journey. And nice enough that nature indicates these areas with nice clouds on top. So that's easy enough to find. So given the setting, we have our little problem here where we're trying to reach the landing zone on the bottom right. And we have to find some path from thermal to thermal to get there. And as we said, we would like to use a heuristic search to find the optimal path on this problem. So one component of that will be a heuristic. And how we get started on that is by looking at the weather forecast for the day before our flight, and we see what the wind is doing. And the forecast tells us that in the lower altitudes we'll have some headwind, so we're expecting the goal distance to be greater at the lower thermals, and higher up in the higher altitudes we're expecting some tailwind, which makes us very optimistic about reaching the goal in a cheap manner. But the actual edge costs are, of course, not given by the forecast, but much more so by the actual weather conditions on the day. And indeed, the forecast was not correct in this case, and the higher altitudes also has a headwind, which makes it the worst option of the two on this day. Now, we will run our planner in the morning before the flight to find the optimal route. And when we do that, we could hope that the search algorithm is smart, and once it discovers the edges on top here, it will see that, or it could see that the edges are quite expensive, and this doesn't really align with our expectations from the forecast of yesterday. And based on that observation, that's during the search, that these edges are quite expensive, we might figure out that actually our heuristic values were not so accurate, and we could maybe improve them, and that we could give them a higher value in this case, which might allow us to prune some significant number of states on the right here and make the search more efficient that way. Right. So this is one very simple example of a dynamic heuristic, meaning that the heuristic values may change during the search. And this is not a new idea, but there have been several approaches that do use this kind of approach. For example, by refining abstractions while the search is ongoing, or by progressing landmarks, which also gives us new information about states we encounter during the search. And the problematic part about this is that these approaches claim to be optimal, to return optimal solutions, but they do so by appealing to the classical result that A star with an admissible heuristic should return optimal solutions. But this is somewhat problematic because, for one, simply admissibility for a heuristic is defined for a static function, for a static traditional heuristic, which is not what we have in this case. And another thing is that the interaction, or the fact that we have a dynamic heuristic, means that there is some interaction between the search and the heuristic, because as we search, the heuristic might change, and then again, the heuristic informs the search, of course, and in that way, there is some interaction between these two concepts that are usually more separate. And this is not accounted for in the classic results of the classic optimality proof. So we're trying to address that, and to do so, we have to make some changes to both the search component and the heuristic. So I'll first tell you what changes we make to the individual components, and then we'll summarize and see what results we get from that. So the first thing, let's look at the heuristic. And in the traditional case, the heuristic only depends on the state. It's just a function that maps the state to some value, to some heuristic value. And in our case, we extend that and generalize that by also adding the information as part of the input to the heuristic. So in our little example, this would have been the information about the wind from which we derived the heuristic values. We would have that wind explicitly as an input to the heuristic as well. And that has some implications. For example, that the traditional properties of heuristics, like admissibility, usually say something like, oh, for every state, the heuristic has to have this property. And according to the definition, we have to extend that as well and enforce that it's not only for every state, but also every possible information that this property holds. And lastly, we define a new property that will become useful later, which tells us that h values may only increase as we gain more information, or it may not decrease. Yes. So that's for the heuristic, and then the second part we have to adjust is the search component, where we essentially do a star search. So on the left, you see a very bare bones, very simplified pseudocode for a star, but the emphasized lines are new, which gets added in this dynamic version of a star. And the two things we're trying to do is, for one, to model explicitly where in the algorithm and how information can be updated. So we saw before that the heuristic depends on this information. And now in the algorithm, we say at what points and in what way information can be updated, which is in this refine and in this update step. And the second part we need, which again, we'll see in a second why this is relevant, is to add an additional check before we expand the state to see whether we actually want to expand the state right now based on the heuristic value. So one weird thing that can happen here that doesn't happen in the classical case is that the heuristic value for a state changes in between the time where we put the state on the open list and where we pop the state. And this reevaluation check checks whether this is the case. So if the heuristic value increased in this time frame, we might decide that this is not actually the best state to expand right now, and we'll pop the next best state and just reinsert the state that we just looked at. Okay, and then to kind of put this together and connect it with the problems we described before is that we extended the static properties to be dynamic by including this information as part of the definition of the property. And we kind of dealt with this interaction between search and heuristic via this information that is used by the heuristic to determine the heuristic values, and that is updated by the search. So that kind of ties these concepts together. Now, what results can we derive from given this framework? And the first one is maybe unsurprising, but that's also a good thing in this case, I would say, is that with our version of the dynamic version of A star and the dynamic version of admissibility, we can still guarantee optimality. And the second part, which has some more unexpected components is that under which conditions can we say that no reopening will happen in this algorithm? And that is the case if we use this reevaluation check that I just mentioned. And additionally, if the heuristic is consistent or dynamically consistent, which would be the expected thing. But additionally, we also need this monotonicity property that the heuristic values can only increase and they cannot suddenly decrease as we get more information. That is also needed to guarantee that dynamic A star does not reopen any states. Okay, and then how is this useful to these approaches that we saw earlier? The idea is that it should be possible to take this result and apply it to the applications that use this kind of dynamic heuristic idea, and to be able to then show optimality in a more formal way using this framework. And very broadly, what you would have to show if you have an application that uses this kind of heuristic and you would like to show that it is optimal indeed, is you could model it in these terms to model it as a dynamic A star search and define a dynamic heuristic in our sense that describes the behavior of your algorithm. And then the second part you would have to do is to show that this dynamic heuristic properties hold initially for the initial information that you have, and that the updates you perform, so as new information gets created, you have to show that this does not violate the heuristic properties, so that it stays consistent, it stays admissible, or whichever of the properties you will need for your result. That's that's probably the how you would go about applying these results to your application. And very finally, some future outlooks, how we could extend this line of research in the future, which would be, we could include deferred evaluation as a different type of search, which we don't cover right now. Or we could look at bounded suboptimality and see if these results also extend to that area. And one thing I would like to do is to treat g-values a bit in a more unified way, because they feel in a way similar to this dynamic heuristic, because it also changes while we search based on the information we gain during the search. And lastly, some optimal efficiency results would be nice, but that seems tough. And with that, thank you very much for your attention, and if you have any questions.
All right, well, we have time for questions. Do we have any questions?
Yes, is there any connection with rollouts? So you're in a state and you have a certain amount of time, and depending on the amount of time that you have, you might have different values. Is there any connection that you can make with any results in that?
So what do you mean? Like what is this rollout?
So in a state you don't know the heuristic value, but you can roll out up to a certain depth and you gather some information.
Okay.
So think about UCP, for example.
That does sound like it would gain you some information about the state space doing this rollout, and then you could adapt the heuristic value based on that. So I think you should be able to model this as gaining information about the state space, and it would be a dynamic heuristic in that sense. Yes.
There might be some results that you can connect.
That sounds interesting. Thank you.
Anyone else? No? Maybe I can just ask, you mentioned there at the end extending to deferred evaluation. What exactly is the extension there? Like, why is deferred evaluation not already captured in here?
That's a good question. Yeah, I think it wouldn't be like a big extension to the framework. It should work pretty naturally.
Yeah, it seems like you would just always do a reevaluation rather than having to check it or something like that.
I would hope it would be that easy, but I'm not sure whether that's the case. So I would have to think about it a more in depth, and kind of the intricacies of the algorithm kind of matter with this kind of thing if you want to stay formal. So it requires some thought, but I'd hope it would be easy. Yes.
So, like, one of the motivations was that we have these updates, of course, in fast downward for the landmark heuristics, and that goes back to the path-dependent and then multi-path-dependent heuristics by Karpas and Domschlag. And over the years, we replace something very complicated and unprincipled with something less complicated and unprincipled. And ideally, we'd have something principled there. And it probably is not going to be some kind of deep result. But the question of where exactly do you do these reevaluations, under which conditions, like this is all just, let's do it that way. Ah, okay. It would be nice to change that. And sort of this deferred evaluation, the fact that you're evaluating sort of edges instead of states makes a little difference there. But I don't think we understand it well enough to sort of really say, is it a significant difference or not? It's all like a little bit